Hello everyone and thank you for joining us. My name is Maitreyi Tirumalai and I'm presenting today with my teammate Fuad Al-Asoli. Our capstone project is on sign language recognition using deep learning for the master's program in applied AI at the University of San Diego under the guidance of our instructor Anna Marbut. Communication barriers between deaf or hard of hearing signers and hearing non-signers will show up in everyday situations: classrooms, customer service, and even healthcare. Many existing ASL tools either rely on fixed pre-trained models or only recognize static hand poses, so they are hard to use for real-time natural signing. In this project, we built a custom word-level ASL recognition system using a 3D CNN that processes short video clips and learns motion over time. Because of dataset constraints, our system currently outputs glosses or word labels rather than full sentences, but the pipeline is designed so it can later be extended toward translation. Overall, we chose this problem to explore an accessible, original application of deep learning that can eventually support near real-time communication in practical settings. We had three main goals for this project. First, to build a real-time ASL word-level recognition model that can work on short video clips. Second, to evaluate not just accuracy, but also how well the model captures temporal motion and how efficiently it runs at inference time. Third, to deliver an interactive prototype interface where we can plug in different models and visually compare their predictions. Throughout, we kept an ethical constraint in mind. This system is meant as an assistive tool or learning aid, not a replacement for deaf signers or professional interpreters, especially in high-stakes settings like healthcare or legal contexts. We use Word-Level American Sign Language Dataset, or WASL, introduced by Lee and colleagues in 2020. It contains about 21,000 short videos covering more than 2,000 glosses signed by over 100 different people. Each clip is a single word-level sign with a JSON annotation that maps it to a gloss label. In our pipeline, we load the official metadata, drop missing or corrupted files, and re-encode all clips to a consistent resolution and frame rate. After this pre-processing, we end up with about 11,980 usable videos. Although the label distribution was highly imbalanced, some signs have many examples while others have only a handful. For the models we'll show later, we focus on a smaller subset of 96 classes with enough examples per class to train and evaluate our 3D CNNs reliably. For training, we start from raw WASL videos, extract frames, and crop the signer with MediaPipe-based regions of interest. These clips are then normalized, augmented, and stored in a consistent format. From there, we create train validation test splits that are as balanced as possible across our 96 glosses, and we train and fine-tune our 3D CNN while logging loss, accuracy, and other evaluation reports. For inference, we support two input modes: uploading a short ASL video or using a live webcam stream. In both cases, we apply the same pre-processing pipeline: frame extraction, ROI cropping, and normalization before feeding the frames into the trained model and returning a ranked list of predicted glosses. In the Streamlit app, we also expose a model selector which can switch between different trained checkpoints like the baseline 3D CNN and the R2 plus 1 D18 variant and compare how they behave on the same input video. Our pre-processing pipeline has four main stages. In stage one, auditing, we run programmatic checks over all 21,000 clips to detect missing files, corrupt videos, and inconsistent frame rates or encodings with spot visual checks for edge cases. In stage two, re-encoding, we standardize everything to 32 frames per second, preserve the original aspect ratio, strip audio, and re-encode to a consistent MP4, so downstream models see uniform input. In stage 3, media pipe region of interest, we use media pipe to detect the signer and crop upper body and hand regions, so later models can focus on the most relevant motion instead of the full frame. Finally, in stage 4, sampling and weight balance, we load the cleaned manifest filtered to classes with enough examples per split and compute class weights to partially offset label imbalance. This gives us a curated subset of classes that is suitable for training and evaluation. I will now hand it over to Fuad to complete the rest of explanation of this project. Thank you.
Thank you, Maitri. Hello, everyone. Now I will walk you through our model training architecture. This is a very high-level visualization of the training architecture we used for this project. Starting with the dataset augmentation, we sample 32 frames per clip, resize them into 112 pixels by 112 pixels, and apply Kinetics style normalization and augmentation such as a flip, blur, brightness adjustments, and cutouts. For the data split, we create training, validation, and testing datasets and load them using the PyTorch with CUDA pinning for efficient GPU training. For the model selection, we tested multiple architectures and selected the R2+1 D18, which is a factorized 3D CNN, pre-trained on Kinetics 400. Each 3D convolution is split into a 2D spatial convolution followed by a one-dimensional temporal convolution, so weights are tuned for that decomposition. Inputs are the same 5D tensors, but with the architecture learn temporal dynamics differently, separates spatial and temporal kernels, and typically converges faster than a plain R3D at the same depth. Our training loops consist of 20 epochs, with Adam Optimizer with weight decay, mixed precision, label smoothing, and gradient clipping. We evaluate our outputs using confusion matrices, class-level accuracy, predictions, and summary reports. On the next slide, we'll see a comparison of our model performances. It's worth mentioning that the baseline 3D CNN achieved around 11% accuracy, which is very close to random guessing. And also the 3D CNN with ByGuru did not really improve that much due to the data limitations. However, our best performing architecture was the R2+1 D18, pre-trained on Kinetics 400, reaching a validation accuracy of 45.3% on our balanced 24 class datasets. This highlights the importance of temporal modeling pre-training for gesture recognition. To showcase the system, we developed an interactive application with the 3 modes: simple, advanced, and live streaming mode. Simple mode helps you to run an existing sample that's already associated with the best performing checkpoint, matching the tensor's architecture. The advanced mode is for you to select and modify the checkpoint, tensor's architecture, and pre-processing and other parameters. And finally, live streaming mode for live translation from a webcam. Our results displays model architecture, confidence score, frame sequence, and extra debugging. To conclude, we delivered the following goals: built a fully working AI-based ASL recognition system, achieved 45.3 accuracy using the R2+1 D18 model trained on Kinetics 400, developed a complete framework ready for real-world applications, and for future expansions, with a larger dataset, we can expand into full sentence translation, while the current system already supports real-time ASL to English pipelines.